Yes, I have started. So, round trip time is very simple, that is 1 millisecond. Then for fraction of received power to transmitted power. So you have, how can I draw here? So steel vessel is there. And then at the bottom there is that transducer, and this is quartz. Liquid steel metal.
Sir, that writing is not coming.
Writing is not coming.
No, sir, it's white.
Oh, okay. Is it coming?
Yes, sir, now it is coming.
Yeah. So we had given that velocity 1.5 into 10 cube meter per second. Then density 5 into 10 to the power 3 kg per meter cube. Power attenuation coefficient is given. It is 0.1 meter per meter. F 1 megahertz frequency is given. So first one is very simple, that round trip time, that is TT 2 into 0.75 by 1.5 to 10 cube. So that is round trip time. So now the next question, next part was fraction of received power to transmitted power. Fraction of received power. So for that we have to use that transmission deflection coefficient at the boundaries as well as this power attenuation coefficient. So for determining that transmission reflection coefficient, we can use this acoustic impedance, which can be computed from the density and velocity is given. Otherwise, it has suggested table 16.1, table 16.2. Those data would be given, table 16.2. (16.1) characteristic acoustic impedance of quartz is given, that is 1.5. One 1.5 into 10 to the power 7 kg per meter square per second. And this one we can compute. This one would be acoustic impedance, rho is given. Five into 10 cube, and C is given 1.5 into 10 cube. So multiply rho into C. This is equal to 7.5 into 10 to the power 6. So now, if from the transmitter, what will happen? The beam will go and come back. So therefore, here there is a reflection coefficient at this point. Similarly, at this point also there is one reflection point. So here the transmission coefficient will be come into picture, and here reflection coefficient and then transmission coefficient. So basically there are the steel quartz steel and steel quartz interface will come twice. Liquid steel and metal, liquid metal and air. Interface will come once. So air acoustic impedance is given in 430. So then the power ratio, received power by transmitted power, would be equal to first transmission coefficient alpha T, that is for quartz steel, quartz liquid metal, quartz liquid metal. This then it will have that continuous attenuation due to power attenuation coefficient, which is given as 0.1 per meter, that is alpha W into L, length that has been transmitted. Then reflection coefficient, that is LS air. Then another will come alpha transmission coefficient while returning, again QLS. LSQ and QL, basically LSQ. Transmission coefficient for power transmission, energy transmission coefficient for QLS and LSQ would be same, because that is R2 minus R1 square by R1 plus R2 square, or R1 minus R2 square by R1 plus R2 square. So that way these transmission coefficients are same, but you have to determine it from this acoustic impedance and all those. So please compute. So alpha T QLS. So that is quartz is how much? 1.5 into 10 to the power 7. So that is 15 into 10 to the power 6. 15 into 10 to the power 6. This is minus 7.5 into 10 to the power 6 divided by 15 into 10 to the power 6 plus 7.5 into 10 to the power 6 square. How much is this? This is 7.10 to the power 6 cancels out, so 7.5 by 22.5. Yes, tell me how much it is. Somebody is there?
1 by 9.
Yes, 1 by 9.
1 by 9.
Hello, sir.
Yes.
Sir, if we are calculating received power, should we also not consider the reflection from the from the quartz liquid steel interface when the signal is entering from quartz to liquid steel?
Huh. Quartz to liquid steel is this one, this alpha transmission, first one.
Yeah, but shouldn't we consider reflection from that surface as well? Because
No,
one will.
no, because it is going forward, so transmission is considered.
But sir, all it is asked that what is the received power, be it from whichever surface, but all it is
No,
asked that.
no, actually, we are measuring the depth. So whatever the first reflection is discounted. Okay.
Okay,
We are only considered about this reflection. So because that will also come as a very short duration time, within that resonance frequency it may come.
yes, sir.
So that has to be rejected. Usually, as we have discussed, that there are matching impedances given, but to make it simpler, this problem does not have that. Okay. So if there is matching impedance, of course, this reflection will not occur.
Okay, sir.
And
And
then
sir,
this transmission will be almost full, and this transmission will be full, and this is air boundary. This reflection is almost 1, because air is 430, only 430, and liquid metal is 7.5 into 10 to the power 6.
yes.
So that reflection coefficient will be almost 1. But
Okay,
we
sir.
will,
Thank you.
here it is 1.9, and then this one exponential of alpha W is given. Alpha W is zero point 0.1 per meter. L, it is going twice, so 7.5 into 2, 1.5 meter. So exponential of 0.1 into 1.5.
So what is that exponential term for? Like I can't understand.
This is for continuous attenuation.
Oh, okay,
That
okay,
B.R. Lambert's law.
okay.
So that is exponential of 0.15. Exponential of 0.15 minus 0.15. Again need to be this my calculator. E to the power x. X minus so how much this is? Is it 0.86 or something?
Yes, sir. Sir, overall it's 0.0956, including the alpha t term.
Oh, you mean to say received power by transmitted power?
Sir, I mean alpha t to the power minus that one is 0.0956.
0.0956.
I mean, sir, by dividing it with 9. So this is correct only, this one. This one.
Okay, this is okay. All right. So then we have this is a power, fraction of power, a power is 1 by 9 into 0.86 into 1, approximately 1 into, again that one is 1 by 9. So how much it is? 0.09 something you are telling. 0.86 divided by 81.
So 0.016.
Oh,
0.016.
0.016, yeah.
106.
0.106.
No, sir. 0.0106. So 0.0106.
0.01.
Yes, sir.
Oh, it is becoming too low.
Sir, are we not
Oh,
considering the...
I think I have done a mistake here. This is reflection coefficient, but actually we have to consider that transmission coefficient that you should have checked, no? Basically, this is reflection coefficient. Okay. Transmission coefficient is 1 minus this one, alpha t 1 minus 1 by 9, 8 by 9. Eight by nine. Also transmission coefficient we can compute alpha t 4, I think 4 R1 R2. Or R1 R2 by that one. So how much this will come? Ten to the power 6 cancel out. So this is 15. 15 plus 7.5, 22.5 into 22.5. Point 88. So this is the alpha t. So 8 by 9 is how much? Yes, 0.88. All right. So 0.64 divided by 81. 0.79. 0.67 is coming.
Sir, we are not considering the power attenuation factor here.
Power attenuation where?
Sir, in calculating this,
Uh-huh.
sir, there is one attenuation factor given.
That is 1.1 per meter.
Oh, okay. Achha.
So that's why that exponential of minus alpha WL, this one is there.
Oh, okay, sir. Yes, sir.
Acoustic impedance we have computed correctly, rho into C. Yeah. Seven 7.5 into 10 to the power 6. But table 16.2 still acoustic impedance is given different. 4.7 into 10 to the power 7. That is of course not liquid still. Density 7.8. Here density is 5 into 10 cube. Yes, so next part is choose the values, suitable values for pulse width. Choice of pulse width. Choice of pulse width. So there are several things. First, we have to see that natural frequency is given 1 megahertz. So therefore, naturally, the pulse width has to be more, much more than that time period of 1 microsecond. That is the corresponding to the natural frequency. We have 1 microsecond. It has to be more than the t omega tfn. Should be more than tfn. So t pulse should be more than tfn. Then it has to be less than the time taken by the travel, that is 1 millisecond. So therefore T pulse, this is TFN is 1 microsecond and this is 1 millisecond. So it has to be in between. Maybe it should be much quite usually when a pulse is excited, there will be ringing effects will be there. So if it is operated at the natural frequency to have the good efficiency, then this will be several such amplitude will be. This will be the nature of the pulse, I think. Sorry. This kind of pulse should be there. So then even if we consider just the two side lobes, it will be one, at least 3 microsecond, at least it should be much more than this. So this could be somewhere between say 10 microsecond to maybe 50 microsecond pulse width can be chosen. Any value can be chosen. However, the travel time is 1 millisecond for this particular height. If we want a resolution, good resolution of this high depth measurement, then the lesser the value of T pulse, that should be better. So, so we have 10 microsecond is good, then corresponding to velocity we can get 10 microsecond will give you a resolution of depth measurement. The velocity is 1.5 kilometer per second. Is it per second? Yes. 1.5 kilometer per second. So this will give a depth resolution. Is 1.5 into 10 to the power minus 2. So it will give 1.5 centimeter. Corresponding to 50 microsecond, of course, it will depth measurement resolution will be lower. Here we are assuming that we can resolve the pulses corresponding to a differentiation of one period. Usually, if you see the shape of these ringing artifacts, so it is often difficult if it arrives within one time period of that excitation. Repetition time, that means successive measurement, we have to cover the range. Repetition. Suppose it is the range is not given, so like here it is 0.75. Suppose 1 meter is the range. Say 1 meter, then repetition time could be greater than 1 meter travel time. Twice that. 1 millisecond is that round trip time. I think, yeah, round trip time is 1 millisecond. need to be greater than the round trip time. So it need to be chosen something should be greater than 1 millisecond, or maybe here it is 1 millisecond. So can be 5 millisecond, 10 millisecond. So it depends on the dynamics, time constant of the change in level. Time constant of the measurement. Measurement update. So time constant is usually for continuously measured variables. Here we are not measuring continuously. Basically we are sending a pulse, waiting for its reflection, then doing some kind of processing and calculations. So basically there would be launching time, which is negligible. So this time would be 4-5 microsecond only. If it is 1 megahertz, and we have 10 microseconds, so 10 microsecond is the launching time. So launching time is 10 microsecond. Then travel time will take some time. Here it is taking 1 millisecond time. And but we have chosen the range to be much higher, corresponding to some repetition rate, suppose 5 millisecond. Okay, so 5 millisecond. So then actually this repetition rate will determine the overall time constant. So 5 millisecond would be the time constant. So every 5 millisecond we can have the measurement. Measurement update requirement. Okay, so next problem is the Doppler problem. So that there you have ultrasonic Doppler flow meter, flow rate of a slurry in a steel pipe is given, 0.2 diameter, again natural frequency 1.5 megahertz. But what is important is that 60 degree. So that frequency shift, you know, delta F. So that delta F is equal to V cos theta into 2 divided by C. So B is given, C take his water. Water, how much is there? Capacity for water 1.5 into 10 cube meters per second. V is given, V is how much is given. V has to be determined. So V need to be determined. So we have volume flow rate. Volume flow rate meter cube per hour. So area diameter is given 0.1 square. So V is volume flow rate divided by area meter per divided by 3600 meter per second. So this is V. So V you can put and then delta F you will get. So like that you can solve this second one. You check the calculation.